6.1 Reciprocal, Quotient, and Pythagorean Identities. So when we talk about identities, the first thing we need to know is what is a trigonometric identity. So this is a trig equation that is true for all permissible values of the variable in the expression for both sides of the equation. So when I look at this, there's a couple key words I need to focus on. So the first one is permissible. This means that anything that's allowed. So we're going to be spending some time looking for values that are going to have a denominator of 0 because that would be non-permissible. I cannot divide by 0, so that's going to affect the values that I choose. The other thing is that when we use a trig identity, we're really using this as an either or an or. So we're going to either use the right-hand side or the left-hand side to help us get to figuring out our puzzle, which is what a lot of these questions end up looking like. So we're already familiar with some identities. We just haven't necessarily called them that. So some of the things that we've done is that cosecant is equal to 1 over sine, secant is equal to 1 over cosine, and cotangent is equal to 1 over tangent. This means that I can interchange the left and the right-hand side, and it's not going to change the value of my equation or of my expression. So those are called the reciprocal identities. I also have the quotient identity. So this is that tan x is equal to sine over cosine, and cotangent is equal to cosine over sine. So example 1 asks us to verify a potential identity numerically and graphically. So we're going to determine the non-permissible values in degrees for the equation of secant theta equals tan theta over sine theta. So this is not necessarily going to be a identity yet. We are checking to see, does this work at specific points? If it does, then we might be able to get to the point where we say, yes, 100% that is an identity. So for part A, we are going to look for when our denominator is equal to 0. So our denominator is sine theta. That means I want to know where is sine theta equal to 0. And that's going to happen at 0 degrees, 180 degrees, and 360 degrees. So I can find this by using either my exact values chart, my unit circle, or I can use my knowledge of what the sine graph looks like and think, where is that crossing my x-axis? So question B asks us to numerically verify that theta equals 60 degrees and theta equals pi over 4 are solutions to the equation. So I'm going to start with the 60 degrees. And I'm going to start with my equation. So secant theta is equal to tan theta over sine theta. They gave that to me in part A. Next thing I'm going to do is I'm going to plug in the 60 degrees for each of those thetas because that's what they told me. Theta is equal to 60. And so I have secant theta is, or secant 60 degrees is equal to tan 60 over sine 60. Now, secant of 60 degrees is equal to 1 over cosine of 60 degrees, which is 1/2. So cosine of 60 is 1/2, so the reciprocal of that is going to give me 2. With the right-hand side, tan at 60 degrees is going to be root 3, and sine at 60 degrees is going to be root 3 over 2. Now, these are coming from my exact values chart. So I'm just going to use that chart in order to actually grab what are those values going to be. Once I have this, I need to simplify my fraction. So if I'm dividing by a fraction, that's going to be the same as multiplying by the reciprocal of that fraction. So 2 is equal to root 3 times 2 over root 3. A root 3 on the top and the root 3 on the bottom are going to divide or cancel out. And I'm going to be left with 2 is equal to 2. Now, my goal here is I'm not moving anything on the right-hand side and the left-hand side. They are stuck on the same side of the equation, equal sign that they start on, okay? And my goal is I would like it to say 2 equals 2 or 1 equals 1 at the bottom. If I get 1 equals 2, that means that this is not going to work for this identity, and it's not an identity. It's just an equation that may or may not have a solution. As we move into doing this with pi over 4, I'm going to start again with that same equation. Secant theta is equal to tan theta over sine theta. Similarly, I'm going to put in my values of pi over 4. And I'm going to, again, use my exact values chart to determine which value should go in here. Keeping in mind that secant theta is, or secant pi over 4 is the same as 1 over cos of pi over 4. So I'm going to have root 2 over 2, and I'm going to do the reciprocal. Again, I'm going to use my dividing by fractions. And as you can see, that I'm going to have 2 over root 2 is equal to 2 over root 2. So basically, this is actually telling me that this could be an identity given this one, or I guess these two different numbers. So it works at 60 degrees and it works at pi over 4. We're not positive if it's going to work at absolutely every measurement that we could put in there, but it is going to work for just these two. Part C, you can do on your calculator on your own. So it asks us to use technology to graphically decide whether the equation could be an identity over the domain negative 360 to positive 360. So what you would do for that is you would actually put each of those in, and you would determine if you think that, so you'd have the left side and the right side, and your goal would be to have only one graph happen. So you would graph the left side, and it would graph the right side directly over top. If that happens, then it is an identity. If it doesn't, then it's not an identity. Example 2 asks us to use identities to simplify expressions. So part A asks us to determine the non-permissible values in radians of the variable in the expression cotangent x over cosecant x cosine x. So first thing we're going to do is we're going to start with that equation. We can't do any, or our first thing we're going to do is we're going to look at our non-permissible values. So cosine x is part of our denominator, and what we're going to do is we're going to look for where is cosine x equal to 0. That's going to happen at pi over 2 plus pi n. So anything that's a multiple of pi over 2, cosine is going to be a 0. So that means that I cannot have those values and still have this equation work. The next thing I need to look at is cosecant, because it is also in the denominator. Now, cosecant x is never going to be equal to 0. And the reason behind that is because I can't have 1 over sine x equal to 0. So we're not actually going to come up with any non-permissible values out of the cosecant. We only need to consider cosine. Part B asks us to simplify the expression. So basically, that's a fancy way of writing is write the expression in terms of sine and cosine only. So I only want to write it sine and cosine. I don't want that cotangent, and I don't want that cosecant. So that means we're going to have to do a little bit of flip-flopping in order to get what we need in here. So the first thing we're going to do is we're going to start with the equation. So I have cotangent x over cosecant x cosine x. Now, I kind of already have it here, but what we're going to do is we're going to pick one piece and replace it with something I know. So we're going to look back on that first page and say, okay, cosecant x is equal to something else. And I'm going to directly replace it in my equation. So instead of cosecant x cosine x in my denominator, I'm going to have 1 over sine x times cosine, and I'm going to write it over 1 for now, x. So basically what I did was I took this cosecant x and I swapped it for 1 over sine x. Now, an analogy I've used in the past is often when you go to a restaurant, you order your meal and they say, would you like soup or salad, or fries or salad? And you can pick either one and it doesn't change the value of your meal. And so all we're doing is we're taking that cosecant, or that salad, and swapping it for 1 over sine x, or that much yummier set of fries that they're going to give you. After we do that, we can actually combine this 1 over sine x times cos x over 1, because that gives us another identity. So we know that those will multiply together, and we have cotangent x over cosine x sine x. And we can look at that, and if we look back on our first page, we have another identity there that tells me, you know what, this top cotangent x is the same cosine x over sine x. So we actually end up with the same fraction on both the numerator and my denominator. As I work through this, I can use my properties of fractions. So I'm going to, if I'm dividing by fractions, I multiply by the reciprocal. And everything here is going to cancel or divide out to being 1. So overall, this doesn't even simplify to being cosine or sine. this comes to simplifying to being 1. Now, this might seem really challenging and like, wow, where did she get this? Unfortunately, with the identities unit, this is something that it just takes some practice. You're not going to get it the first time. You're going to have to play and just get really familiar. It really comes down to a lot of times when we are solving identities and working with identities, it's much like building a puzzle. Much like doing a puzzle, identities, we have to look for the things we have in common. So I started this jigsaw puzzle here online. I have the outside there because I know most of us start with the outside. And I want to find out which this piece is here. So I'm going to do a few things. I'm going to look for what do I have in common. Well, I have some gray here and some really light gray, almost approaching on white here. And I know that roughly this is probably going to have some red on these corners. So I'm going to go look at my pieces and I'm going to look for things that have those as well. So I have some of this light gray and darker gray and the red. And so I might try this one and it might fit. And that's good. But sometimes when we pick and we're trying to decide which piece is going to go in which spot, we're going to try something that doesn't work. So, oh, that didn't work. This one. So this one here, if I try to put it here, it might look initially like it would work. It's red, it has the opening at the bottom, and it sticks out on this side. And so I might try and fit it in there. But it's not quite the right piece. And so I need to go back to my pile of pieces and decide, okay, this one didn't work, but it's got to be something like this. It's got to be all red. And so I might find another one. And so this one here looks like it's going to be the piece that goes there. And so as I do that, that's going to help me because, yes, I know that this is no longer the right piece there, but it did help me. When I set it there, it looks like it might blend. It has the lighter red at the top. It has the darker red at the bottom. It's all red, just like the pieces around it. And so I tried that out, but it didn't quite work. And that's going to happen often when you do identities. It's not going to be something that you get the first time round. In chapter 4, we studied the unit circle. We used our diagram and we could determine the Pythagorean equation around that. So you'll see that this is that same diagram that we have. Now we're going to put a couple of labels on here just to refresh. So this distance here is going to be the distance x. This distance here is going to be the distance y, and I'll fix where that's located in a second. And our hypotenuse is 1 because it's a unit circle. So that means that we are going to have a hypotenuse of 1 or a radius of 1 at all times. Now, we also remembered that this cosine is our x-coordinate and sine is going to be our y-coordinate. So these are things that we've sort of talked about. They're just being refreshed here because we are going to use them to develop the next idea. So if I want to use this for a Pythagorean equation, I'm going to find the length of the hypotenuse. And so this hypotenuse, I'm going to use the equation of a circle, which is x squared plus y squared equals 1 squared in this case, because our radius is 1. And as I go through and solve this, I can say that my x value is cosine. So I have cosine theta squared, and my y value is sine, so sine theta squared, and that's going to be equal to 1. And when I rewrite it with our squares in between the cosine and the theta, just like we talked about in class, I actually come up with this equation. So cosine squared theta plus sine squared theta is equal to 1. This is the basis of the Pythagorean identity. So this is another thing that is always going to work no matter which value I put into those equations as theta. This is going to be something that holds true. So this is our first Pythagorean identity. Sine squared plus cos squared equals 1. Now, I rewrite it with sine squared first because typically we think about it in terms of SOHCAHTOA, where sine is first. It's typically the first one that we learn. Although because it is addition, the order doesn't actually matter. So really this one or this one, they mean the same thing. This just tends to be the way that we write it more often. So there are actually 3 forms of the Pythagorean identity. They are cos squared plus sine squared equals 1. Cotangent squared plus 1 equals cosecant theta, or cosecant squared theta, and 1 plus tan squared equals secant squared. Now, you can use the other identities, the quotient and the reciprocal identities, along with this one here, the sign at the top, and you can actually build all of these together. We're not going to go through that, but if you do want to do that, come see me and we can sit down and actually build those three. I just don't think that the time spent doing that is very useful. We can spend our time later playing with those types of things later on in this unit. So example 3 asks us to actually use this Pythagorean identity. So it asks us to verify that the equation cotangent squared x plus 1 equals cosecant squared x. Just make sure it's true when x is equal to pi over 6. Now remember, x, theta, they're just variables. We can interchange them and use whichever one we decide. It's not really set in stone, so you'll see that they'll use them interchangeably. So first thing we're going to do is we are going to write out our equation. So cotangent of pi over 6 squared plus 1 equals cosecant of pi over 6 squared. So all I did was I replaced my x with my pi over 6. The other thing I did was I said cotangent pi over 6, whatever it's equal to, whatever number that's equal to, I'm going to take that and I'm going to square it afterwards. So I did kind of rewrite that squared outside of the brackets. The next thing we have is the actual values. So I'm going to use my exact values chart, knowing that cotangent is the reciprocal of tangent. So I'm going to have, instead of root 3 over 3, 3 over root 3 plus 1 equals, instead of 1/2, I'm going to have 2 over 1. And so my squareds are going to stay there. My next step will be to apply that. So just a refresher on how we square fractions. So we'll square the top and the bottom separately. So 3 squared is 9, and root 3 squared leaves us with 3, plus 1 equals 4 over 1. 3 plus 1 equals 4, and woohoo, 4 is equal to 4. So basically what we found is that, yes, this works for pi over 6. We don't know necessarily that it'll work for every other number, but we do know that that one is going to work here. Typically, you can prove them for all values. It is a lot more challenging, and so we don't typically cover that in this course. We will do some where we use what we do know and just assume or use what other people have proven to build our own. But for now, we're just going to say, you know what, this works for this value especially. Part B asks us to use the quotient identities to express the Pythagorean identity in terms cos squared x plus sine squared x equals 1 as the equivalent identity of cotangent squared x plus 1 equals cosecant squared x. So basically, to convert the one we found above to the one we used here. We're actually not going to do that today. We're going to wait to do more of those types of things later on in this unit. Your assignment is located at the bottom of your page, so 1 to 8, 10, 12, 13, and 16. Please remember, yes, you will probably get frustrated on this. There is no magic way for me to help you. Think about building the puzzle. What piece do you have? What do you need? What do you know that has those in there? That's going to be the key to understanding and really being able to master this content, is staying calm and deciding, you know what, I can do this, and just take your time and keep trying, because it takes practice and there's no other better way that I can put it. So have fun on your assignment.